You validate your...
I know, it's like validating my career choice or something. Any questions? You okay?
We have to memorize those things. We have to memorize
Those conversions for polar? Yeah, they're in all honesty, I think the only one you really need for the test is x squared plus y squared becomes
R squared.
Yeah.
Cool.
But you know, it's worthwhile if you
I don't remember why. I don't remember why I wrote them down.
They're probably on your public notes. That's it.
Probably somewhere in there.
All right. Now this, yes sir, yes sir. No, no. I thought someone had a question. Okay. No picture with this last one. Now I'll put a picture up here eventually. Okay, I want to show you what the solid looks like. But and I'm sorry that the context is all volume. I don't mean for that to be your only frame of reference for triple integrals. It's just one of the few things you can actually do to help you see what a triple integral does. Looking at the triple integral homework, the supplemental problems I've posted online, I mean, there's a handful of problems where you're given the 3D solid that I want you to find the volume for, setting up z, x, and y limits. And so if you've got a picture, and these pictures are probably easier to see on the computer screen than right here, like this one, if you did the z limits first, you go into the base, it's on the xy plane, you can kind of see those skewed lines of the parabola at the base, and then this tilted plane z equals 2 minus y is on the top. So you're going from the xy base, xy plane base, to this tilted plane on the top. And so that should be pretty consistent for your z limits. And then when you flatten it down, do you see what curve's going to be down there in the xy plane underneath it? That's the important part. Make sure you can, you know, I guess undimensionalize it one step backwards to 2D. Can you see what that underlying region for the base would be?
Parabola.
Yeah, this right here, this x equals 4 minus y squared defines the lateral cylinder boundary for the top, and that becomes the parabola in the base. And then what's the other bound? The parabola and what else?
And the x-axis y.
Oh, be careful. I think that's the y-axis. Yeah, the y-axis is the other part because you got these little dotted lines right there to help you kind of see through it, to let you know that there is a proper corner there. It stops at the y-axis over there. So when you project it down to the xy plane, try to use those little skewed lines and those dotted, you know, x-ray vision lines there to help you sort of see through it to see what the underparts are. But not all your regions are going to have a picture of the solid. So I need to kind of see if you've been paying attention to your grammar lesson on prepositions. All right, here we're finding, and also, again, I mentioned the context isn't always volume. See, some of the first problems are just, boom, here's a triple integral, here's the function you're integrating, there's the limits, just integrate it. So it's not always the triple integral of function one. I mean, you actually, you know, have some functions here that you can integrate and then plug in the limits and evaluate it like a regular double or triple integral. So I'm just sorry, I just realized now that my lesson's a little bit skewed toward all the examples being volume, and I apologize about that, but you know, it still sets up the same way. The trickiest part of the triple integral is most often not really the integration, it's the visualization of your solid that sets up your z, y, x limits. So find the volume of the solid lying inside, first preposition of the problem, lying inside the cylinder, and then whoa, y equals 4 minus x squared. What's y equals 4 minus x squared in just xy plane?
Say parabola.
Yeah?
Is it downward?
4.
Y equals 4 minus, so
So it's a downward parabola.
so it's a downward parabola,
Originating at y equals 4.
originating, shifting up to the y equals 4 value for its y-intercept and opening down. Okay, now, this is described as a cylinder. Why?
Because it's infinite on those.
Is that the top?
Yes, because this is in the xy plane where z equals 0. Now, all of you, you need to kind of take your notion of what a cylinder is, you know, paper towel roll, you know, toilet paper roll, you know, gift wrap paper roll, things like that. That is a circular cylinder. If you're just talking about anything that's a cylinder, it's any kind of three-dimensional shape that's generated by a two-dimensional curve running parallel to an axis. See, if this is what this curve looks like at z equals 0, what would this surface look like at z equals 1?
Same.
Exact same thing. One click higher, the exact same parabola. Okay, at z equals 3, same parabola. At z equals 10, same parabola. So opening around the z-axis, the reason this is called a cylinder is because it's the same two-dimensional cross-section every z value that you go. So in 3 space, this cylinder would have the same properties. It'd have a y-intercept at 4. It would open along the y-axis going backwards like this. So here's a skewed version of what this cylinder looks like. But it just runs parallel to the z-axis. So it looks something like this. You see? It's essentially like a sheet of paper wrapped around the z-axis, with the z-axis inside the parabola's curvature.
And that's a cylinder?
Didn't you draw that on
That's
the
a
Y?
cylinder. Pardon?
Didn't you draw that on the Y?
No, this is the z-axis. See, this is the projection in the xy plane.
That's to the negative.
Notice in your framework here, this is the x-axis, this is the y-axis. So let me see. So here's the xy plane projection of it. Here's y equals 4. And the x-intercepts are at plus or minus 2, so that's noteworthy also. So just in the xy plane, that parabola that's described as a cylinder would look something like this. Okay? But since the equation for the cylinder is independent of z, you're going to get this exact same parabolic cross-section at z equals 0, z equals 1, z equals 2, z equals 3. So that means it generates a surface that runs kind of parallel to the z-axis. It's sort of wrapped around the z-axis like an infinitely tall sheet of paper, okay? And technically infinitely wide sheet of paper. So it looks something like this as you wrap it. So that every cross-section produces the exact same parabola you see down there in the xy plane. Can you see? Maybe. So it's kind of like that. And that's why it's described as a cylinder. Cylinders aren't always circles. A circle is a circular cylinder because it's generated by a circle of the xy plane running parallel to the z-axis. If you took a sine wave in the xy plane and ran it parallel to the z-axis, what would it look like as a surface?
Like a tin roof.
It's corrugated metal.
Corrugated metal.
Corrugated metal.
Corrugated roof. Yeah, like the roof of a Quonset hut or something like that. It'd look like an infinitely long sine wave sheet, like a piece of corrugated metal. Yeah. So anything that's technically a cylinder. It's a sinusoidal cylinder, I guess, because it's generated by a sine wave. This is a parabolic cylinder. It's generated by a parabola. Toilet paper roll, circular cylinder, because it's generated by a circle. So that's why that's called a cylinder. Okay, but again, the solid lies inside. Can you get the notion of being inside this cylinder versus outside of it? Where do you think the locative inside is going to put you? If you were on the xy plane standing inside the cylinder, where do you think a good place you'd be? Where's a point that'd be inside the cylinder? The origin. If you were on the origin, you'd be inside the bowed curvature, inside the curvature of the parabola. So I would say inside the cylinder is anything in here. Okay? So in the parabola. Or I guess in this frame of reference, underneath the parabola. So you're inside the cylinder, you're lying under, another preposition, helps us fix our positioning in space. You're lying under the plane y plus z equals 4. So y plus z equals 4 is a plane up here somewhere. The reason I know it's up here is because our region lies underneath it. So up here on the top somewhere is a plane y plus z equals 4, which is not a parallel, it's not a flat plane, it's a tilted plane because it's got x's and it's got y's and z's in it. So it'll cut into that as some kind of tilt. And then you have these statements. Y is greater than or equal to 0, which will kind of cross-section certain things out. Z is greater than or equal to 0. So I'm lying inside this parabolic cylinder, I'm lying underneath this plane, but I'm only in the space where Z is positive and Y is positive. What does that hash out here?
So you
Bottom right.
Top right?
Yeah, this side over here.
Yeah, so positive y-axis is here, okay? Positive z-axis is here, okay? So does it have any inequality stipulations on x? No. So if you look at this, y is positive here, z is positive here. So you can include those negative 2 and 2. So it looks like we've at least got this and all this being the base. What does the top of the solid look like? What we're lying underneath. Again, those prepositions tell you everything. You're underneath that. So without even drawing the solid, let's go ahead and commit to our limits. Who do you want to do first?
Z.
Z. Z goes from where to where?
And 0 to 4 minus y.
0 to 4 minus y. Why do you know you start at z equals 0?
Because it says anything greater than 0.
Because the z values in our solid are greater than or equal to 0. So z equals 0 is the base. We're going above that, and we're stopping at the plane z equals 4 minus y. Okay? And then we flatten it down where?
To the x and y.
To this. Yeah. If you flatten it down to the xy plane, you're technically now just dealing with the two-dimensional parabola. You don't have to call it a cylinder anymore. But a parabola with 4 y-intercepts, well, a y-intercept of 4, excuse me, not 4 y-intercepts, that would not be a function. A y-intercept of 4. And opening down, y is positive, so that's why we're y greater than 0. You're only on the positive y-axis. There was no stipulation on x, though. So that means x could be positive and negative. So this is our underlying region. Who would you want to commit to next?
Why?
Y. Yes, y, not y, but yes, y. And the reason why y is because, well, I guess for convenience, that curve is already defined as y being a function of x. So y goes from 0 to 4 minus x squared. And then what are your x limits going to be? Yeah, negative 2 to 2. Because there was nothing involved, restricting x to being positive, so you're not guaranteed to be all in the first octant on your solid here. So without any restrictions on x, that might be a tricky thing for some people to pick up on. The only other thing you need here to let you know your first octant is either the words first octant or x greater than or equal to 0. If your description involves x, y, and z being positive, you're focusing only on the first octant chunk. So if I did overlap all this together, the z-axis is technically going vertically from here. This plane has a z-intercept of 4, and it would meet this base, making a shape that looks something like this. Okay, bear with me. That plane goes from a z-intercept of 4 to a y-intercept of 4, so it happens to be kind of like a triangular connection right there. It would connect down here like this. And this cylinder that cuts the walls of the solid would actually wrap kind of sideways up into that plane to give you something that kind of looks like this on the top. So that sort of shoehorn thing, let me go back and maybe do it in blue. So if I outline in blue what our solid is, this is what we're actually finding the volume of. And unfortunately, folks, I do not know of a volume formula for this particular shape. So our 3D solid is that critter right there. Flat on the xy plane, flat on the top. It's slanted, but it's flat on the top because that's the plane y plus z equals 4. Flat on the back, where it meets the xz plane back here, there's a flat square back there. So you got 4 flat surfaces, but then you got one curved surface that's cut out by that cylinder, defining the laterals. Right around there. So I have no idea how to find that volume using anything familiar from geometry. But I bet it involves thirds. Like the cone, 1/3 base area times height. Anyway, but let's just set up the triple integral. We got the limits. Our triple integral will be for the function 1. Anything polar going to come out of this? Probably not. That's not really circular. I don't see any x squared plus y squares popping up anytime soon. So it should just be triple integral with these limits for just an integrand of 1, and we're committing to dz, dy, dx. Okay. So, we just got about 4 minutes left, so just in time. If I integrate dz first, z is my antiderivative. My limits are 4 minus y minus 0, so that was painless. If I integrate this with respect to y, I get 4y minus half y squared with 0 to 4 minus x squared limits. So algebra ensues. Plug in those limits for y. I haven't lost anybody yet, have I? You're all still here, but on the computer's over here. So plug this in for y. It's going to be 4 times 4 minus x squared minus 1/2 4 minus x squared squared. The lower limit annihilates everything. So I'm just going to do my bookkeeping here real quick. So when all is said and done, we're integrating negative 1/2 x to the 4th, that's our highest term. Then we have a negative 4x squared with a positive 4x squared, loving that. And then 16 minus 8. So that should simplify to negative 1/2 x to the 4th, negative 4x squared plus 4x squared, gone. 16 minus 1/2 of 16, most often 8. So that should be what we're integrating by the time we get to x. And x's limits were negative 2 to 2. Even function, symmetric interval, what you want to do? You have no idea what I'm talking about, do you?
Even
Okay,
function,
if you do,
symmetric interval.
that means 0 to 2, double the value. But if not, it's okay. Just do your x antiderivative, negative 1/10 x to the 5th plus 8x, negative 2 to 2. When you plug in your 2, negative 32/10 plus 16 minus, and actually you get positive 32/10 minus 16. So watch out, it's tempting to say some stuff goes to 0 here. That's the whole reason why that trick is kind of cool, to double your limits from 0 to 2. But actually you get negative 64/10 plus 32. So 320 minus 64, what's that?
It's like, it ends up coming out to 288 over 5.
288 over 5? I will take your word for it. Because double that, that's 576, 64, 320. Oh, that is right, yes. Okay, thank you very much. And funky thing is, you know, well, no, I guess it's not as funky as I thought. You know, this particular solid, it doesn't have anything circular about it. So you kind of anticipate pi possibly showing in the volume, but no, just a rational number, 288 over 5 is the final answer. Sorry, I just zoomed out to show the original picture. One problem I want to mention to you. Oh, poo! Hang on. And this is a good one. It's the last problem on your triple integral homework supplement. Okay. These last two, you're not given pictures of a solid that you're finding the volume. Okay. Here, number 12, it's a paraboloid opening upward from the origin of the xy z space opening upward, meeting a paraboloid opening downward. So that kind of looks like maybe a capsule. Okay. So there's an intersection up here that's not in the xy plane, but when they intersect, you'll want to project that intersection down to the xy plane, because most likely that's going to be what kind of shape?
Circle.
Circle. So maybe you'll get involved with some polar on that one. It's number 50 that's the real bugger. You want to find the volume of the region enclosed by this cylinder. Now keep in mind you're in 3 space. X squared plus y squared equals 25 is what kind of cylinder in space?
Circular cylinder,
Circle
radius 5.
wrapped around the z-axis, because this equation is independent of z. So you have a cylinder of radius 5 wrapped around the z-axis, and you want to intersect it with a horizontal cylinder that's wrapped around the y-axis. See, this would be in the xz plane, a circle of radius 5. So it's kind of like you're finding the volume of a
Sphere.
well, not a sphere. Because keep in mind, if you're looking down on this from the z direction, you'll see a circle. If you're looking from the y direction, you'll see a circle. But if you're looking from the x direction, you see a square. So you're kind of looking for the volume of a pipe junction, where cylinder PVC here meets a cylinder PVC here. They both have the same diameter, and you're looking for, you'll see a square cross section this way, circular cross section this way, and a circular cross section that way. Now, if you want a real challenge, mix it with the cylinder of radius 5 wrapped around the x-axis. Yeah, there you go. Find the intersection of 3 pipes intersecting in space that all have the same intersection at the origin radius 5.
Would that be quadruple?
No, that would still be a triple integral, but it's hard as heck to figure out what your top is. Because you have, sometimes you have this being the top, sometimes you have the other one being the top. But maybe you could use some symmetry there. Maybe something involve a 16th. symmetry. Alright, anyway, y'all take care, enjoy this, study hard, get that test done this week, and I will see you on Thursday if not sooner.
When do we